Okay, why don't we get going? As I said, this is Craig from Moberg Analytics. Thank you again all for joining this, our fourth in the series of webinars around neurocritical care AI. I see a bunch of our European friends are out there again, so we thank you for joining on your Friday evening. I hope you have a beverage in front of you. And so let's kick it off. Um, just wanted to reiterate kind of why we're doing these. Moberg, Dick Moberg's companies for 40 years have been focused on this problem, first with the CNS monitor and Moberg research, and and consolidating all of the devices that you use in the ICU. The new company, Moberg Analytics, now focuses on the data piece of that equation. And really the end goal is to help understand brain injury and to help you manage guidance for the patients. And that is a big mission. That is a hard thing to do. I think it's probably one of the hardest problems on the planet to solve. And our goal as a company really is to build tools to help you. And these webinars are an extension of that goal. So we are providing tutorials. We're getting some good speakers to come and share their experiences with you, give you some sample data and tools to use so you can start to apply these techniques to your own problems in your own data. Also, next year, we're going to be kicking off some small starter grants of cloud time, of tools, and guidance to help maybe get these projects off the ground. So look for these in 2024. We will be announcing them in our Neuroscience Monitor newsletter, which if you're not already subscribed to, you should be. And we'll give you a link for that later in the presentation. Also, we would love some feedback for these webinars. I think we sent out a feedback survey. If you would like to give us some feedback on what you like, what you maybe don't like, what would be more helpful things you'd like to see, if you would like to be a speaker, if you would like to share your problem that you've solved, it would be fantastic. It's always great for us to kind of share the webinar with people who are out there in the field applying this stuff day to day. So there's a bit.ly link and a QR code if you want to jump to that survey at any time. So this is where we are in the progression of webinars. We had Ed Kim in sessions 1 and 2. Ramon Diaz-Aristia talked to us in session 3. Today, we're going to look at GOS-E prediction using some of the Boost 2 data. The schedule for 2024, we're still working on. We will be announcing it. I'd just like to say thank you very much for attending this latter part of 2023, and I hope you all have fantastic holidays, and we will be back in 2024 with more webinars. This is being recorded, and the recordings are going to be made available on the website. If you have questions, please put them in use the Q&A feature of the Zoom room. Today, we have a fantastic speaker, our own Ethan Moyer. He is one of the most amazing guys that I've ever met. And he is our director of product development. He started off a few years ago at Moberg as doing one of the very amazing Drexel internships. And he continues to amaze us all on a daily basis with his the ability to do so much work at such high quality, at such speed, and is a constant source of ideas and inspiration. He keeps Dick and me on our toes and a bit younger, if I dare say so. So with that, and today he's going to go, as I said, he's going to go through some GOS-E prediction using some of the Boost 2 data. So Ethan, I will stop sharing and the stage is yours.
Thank you very much, Craig, for those kind words. Definitely put a smile on my face on this nice Friday. I'm going to share my screen, and I first want to start off with this image. It's kind of how data scientists agree that they spend their time, or if you survey data scientists, you spend a lot of your time not even doing the AI and ML and all those cool things that people usually associate with that topic. And so the reason I'm showing this is because in the previous webinar, we spent a lot of time visualizing the data, which, it takes about 1/5 of the time of the whole data science pipeline. And more of this webinar will be focused on visualization, of course, and also data cleaning. And then we'll get into some of the model selection, scoring, training, and then I could talk a little bit about deploying models as well. So this is the Jupyter notebook I put together. Week 4, and we're focusing on predicting Glasgow outcome score, extended the GOS-E scale for the Boost 2 patients, for the cohort of patients that we have. And I'm going to go through this slowly. There's some stuff that I've included just as like nuggets of information that I think would be useful. And I'm hoping to kind of teach you guys how I see data science from more of a software engineering perspective, because often when I look at GitHub repos that are online, some of them are like structured in an unfamiliar way that makes it difficult for people to pick it up and integrate into their systems. So the main packages we're using today are scikit-learn. And I actually have these, I didn't write all this out. These are generated from Google's generative AI through a Google search. So this is just for reference. It's a toolbox that allows you to apply supervised and unsupervised learning techniques, such as like k-means clustering. It likely does PCA, linear regression, logistic regression. We'll touch on one of these today. It's a great Python tool for using a lot of those models and other sort of ML tasks. NumPy is effectively a Python wrapper around a bunch of C libraries that make navigating data really easy. And then Pandas is a library that we used last time, and it's wonderful for organizing, manipulating data, kind of like what you would do in Excel, but with programming. Like we did last time, we're going to install the packages. One thing that I want to highlight that's often good for version control is specifying versions. So you can rely on just installing NumPy or Pandas or any package just out of the box, and pip will go and grab the latest version. But a lot of the times that I've found for our software deployments, it's very important to keep it at one version, because if it's not broke, don't fix it. And unless you really need a new function or a new capability, there's no real reason to change it. So I just want to mention that. We've learned the hard way here at the company about not controlling versions effectively. So the first thing I'm going to do is import all of our modules. You can see we're using some stuff from sklearn. We're going to focus on logistic regression and talk a bit about k-fold cross-validation. I think that's going to be an important concept to cover in this webinar. I'm bringing in NumPy and Pandas, matplotlib, as well as this other utility that I really love called prettyprint. It just makes things look much nicer. Setting the data, this is pretty similar to what we did last webinar. We're effectively reading in a CSV file, and I can actually show you what that looks like before I do anything with it. So this is the data frame that Craig put together last time, and this is what will be available on the Boost 2 Connect workspace that we're working on getting situated up for everyone. And the first thing we're doing is really building a pivot table and removing null values, cleaning it up a little bit, and representing the ICP and PbTO2 measured in millimeters of mercury for both of these columns on a per minute basis for each patient. And I can use matplotlib to visualize the signal. So this is a really naive way to do this, but effectively I'm just taking the timestamps associated with patient 1001 and the ICP signal associated with that patient as well, and graphing it over time. Now, this is something that I might want to do over and over and over again. So I took that and I built a function around it. So I just created a function called plot patient. It takes a input data frame, the ID of the patient, and then the modality that I want to look at. And I tried to be extra careful about building this function because I want to make sure that if I supply any arguments, there will be no unexpected behavior. So the way I do this is by first checking that the inputs are correct. And I could even do this in a lot better way by checking that X is also a data frame, because that's what we're expecting it or assuming it to be in the function. So this function is really designed so that I can provide any sort of patient number or modality that is in the data frame, and it'll graph it for me. So I'm doing the same thing for patient 1002. I can do it for 1001 and get a similar plot to what's up here. And if I type in a random number, it gives me this, my own custom exception that 12 is not in the data set, which is very useful. This is 1003. And then I can do the same thing for PBTO2. And looking at the data, you can see there's some obvious issues. It's spiky, right? There's a lot of artifacts. And in this series, or in this video at least, this session, I'm not covering artifact reduction. We have a lot of techniques here at the company and under our tool belt with other people working with for removing a lot of these artifacts and smoothing it out. You could apply like a rolling mean or the other sort of techniques to smooth it out so that you don't get a lot of these spikes that come from the measurement of the signal. I didn't include that in this webinar, but I will in the future. So it's just interesting to look at the data. I think it's cool. The next thing we're going to grab is the study groups. This is just a mapping between what patient belongs to what group from the Boost-2 protocol, so whether they were managed with only ICP or with PBTO2 and ICP. And then Ramon Diaz-Aristia sent me an Excel file, actually, and this Excel file contains tons of metadata about the patient population that we have. And this is what it looks like. Now, the columns aren't really that discernible. Luckily, he had a section in that spreadsheet that actually contains what these represent. And I'm going to go through these pretty quickly. So for each patient ID, there's some summary metrics. And I'm going to focus on these 4 for PBTO2 and these 4 for ICP. The group corresponds to the treatment group. And then this is the outcome measure that we're trying to predict. And then there's another metric for the amount of days that they had ICP monitoring and the amount of days they had PBTO2 monitoring. So first things I want to define is area under the curve. That is the amount of time that or the amount of area under a certain threshold. So let me go here. So area under the curve is effectively, if I have a threshold of 20 for PBTO2, I would be most concerned with how much data is underneath this region. So underneath the curve, it's the sum of all these, all this excursions below 20, because that's the threshold set by the Boost-2 protocol. And then the average depth is the AUC divided by the duration of monitoring time. So it's just a derived metric from this area under the curve concept, and then it's normalized to how long that it's been measured, because of course, if you monitor for a longer period of time, you're more likely to have more area accumulated. So in terms of these first 4 columns that I talked about, we have PBT min, which is the number of valid PBTO2 readings. And they likely determine this through some sort of artifact detection algorithm or from labels that the CNS monitor actually gives the data. Then we have the percentage of time that PBTO2 is below 20. That's a metric that they included. They included the area over the curve, so the amount of area that exceeds that 20 threshold, and then the average depth, which is just a normalized metric, a normalized measure of that area measurement. So they do that for PBTO2 as well as ICP. So for instance, the number of minutes of valid ICP readings, I'm guessing they took this entire length right here. And then I realize there's a graph of PBTO2, but they're looking at the percentage of time that ICP is above 20. So I just did an estimate here that this is no more than 5%. And then the amount of area under the curve is the amount of area, or the amount of the excursion times the percentage of time that exceeds that. And then the average depth is just a derived metric from those two variables. So I created another function here that plots a scatter plot with a trend line, and it also calculates the R correlation coefficient. And I'm able to take some of these metrics and see whether they're correlated with one another. This is kind of after you visualize the raw signal, you want to check for correlation, because measurement modalities and features that are highly correlated with one another actually should be excluded from a feature set. And really what we're doing here is we're trying to take the raw signal and build out a feature set. And usually I use a cutoff of like 0.9 or 0.95. The reason you do this is because each feature is assumed in a lot of these models, like linear regression and logistic regression. A lot of these models are assuming that the inputs are independent of one another. So looking at ICP 20 PCT which is the percentage of time that ICP is above 20, and the percentage of time that PBTO2 is above 20. We can see that they have there's little correlation between the two, which means that they each add their own set of information or information to a model. They both contribute different things, which is important. We want features in our data set that contribute different types of information to what we're predicting. And I included a couple examples of just crossing different combinations. And this one is not, this one's expected because they're both measures of PBTO2. This one's the excursion of over 20, and then this one is the area over the curve. And one is derived from the other. So it's a nonlinear feature, and that means that they're going to have some relationship. So this one would be removed in a formal ML model. Yeah, so looking back at the metadata, what I'm going to do is I'm actually going to extract those 6 features that I actually care about, in addition to the group, which is this column right here. This is the group there, and this is a treatment group. So I'm using these 6 features here, 8 features with the treatment group. And I'm building a 2D matrix where each row is an array of those 9 elements. And then the Y target is going to be this column right here, which is GOS-E. And then I'm doing a cutoff at about 4 to binarize it, because I'm doing a binary classification of GOS-E, so whether it's below or above that threshold of 4. And this is what X looks like with all that data extracted. And this is what Y looks like, all that data extracted. Typically, you build an X for features and then a Y for a target output. The next thing I'm doing is I'm building a function that does k-fold cross-validation. K-fold cross-validation, well, first off, in typical machine learning, what you do is you build a training set and you build a testing set. And you train the model on the training set and then see how well it performs on the testing set. More state-of-the-art, I guess recently, more people have been using k-fold cross-validation, where you move what the training set is and testing set is, so that you can get a more representative feel for how well the model actually performed. So I can actually draw here. I think that would actually work really well. So let's say that we have, this is our data set, and let's say we're doing n equals 5, so we're doing 5 folds. And we split it up into 5 sections. Maybe in the first round of k-fold cross-validation, we take this first section and we make this the testing set. And then we train on the other 4/5 of the data set. And then in the next round, we would change which section is the testing set. So then maybe the testing set is this second segment, and then the training set is this first segment with these 3 segments. And you're just shuffling what is used for training and testing, and then averaging the results in the end. Drawings, cool. So this function really just sets up the K folds, the amount of folds that we're using, and I have this set at 5 right now. And then for each fold, it's assigning and extracting the training set, the testing set. And in this case, I'm using a logistic regression to train the model and then predict from the testing set. And then I'm comparing what was predicted to the actual values in the testing set. And the main score that I'm grabbing is called the F1 metric. So I have a bunch of explanations and definitions of what these are. So the F1 score is actually a combination of precision and recall. Precision is the higher the precision, the better the model is at detecting or not detecting false positives. And recall is a measure of how well the model is not predicting false negatives. Usually there's a trade-off between the two. And the F1 score is a reciprocal relationship between precision and recall. So if you are producing an F1 score closer to 1, that means that you're balancing the precision score and the recall score very well. The reason that I wouldn't use accuracy in this case is because accuracy can be heavily biased by imbalanced classes. So it's likely that we have more GOCs above 4 than we do below 4. And I didn't test for that. But in the case where classes are balanced, accuracy would be a good measure. But in the cases where it's not, you should be careful when using accuracy because it can be heavily biased by that imbalance problem. And there's other ways to fix this too that we'll likely cover in future webinars. One thing else I'd like to mention about this function is I actually have a step in here that scales each column. This standard scaler transforms the columns so that they're on a scale of 0 to 1, so that when I'm feeding them in to the model, they're appropriately scaled and not the model doesn't feel like they're seemingly unbounded. And well, this might not be needed for a logistic regression, or it might not be as needed for a logistic regression. These scales can influence other model types like a neural network, which we may do in a future webinar. And the reason I'm creating a function here is so that I can use this over and over and over again without necessarily having to copy so much code. Instead, I can just run this function and it generates the results of the 5 folds. And we can see that the average F1 score is 11%, which is actually, it's not great. It's not something you want to deploy. Unsurprisingly, it didn't perform well on the feature set that I got from the Boost 2 coordinators. And the reason why I'm highlighting this is kind of the first use case is because the steps to actually performing and running the model are highly influenced by the data you give it. So in this case, I'm giving it data just kind of that I got off the shelf. Someone gave me the data set, I'm plugging into a model, and unsurprisingly, it's not doing very well. What you need to do is you need to spend time engineering your features. And feature engineering is a very difficult task because you have to either have clinical expertise of what is relevant for what you're predicting, or you have to build models that can automatically or seemingly automatically extract features from your data set. So I spent some time engineering my own features, and they're similar but not the same to what was shown in the last section. This is just some software engineering what I'm doing is I'm defining a class that will store less than or greater than, and then it allows me to actually design these functions in a much safer way. So the first function I'm doing is taking a data frame X and returning the area that it exceeds that threshold by using a rectangular or Riemann sum. And the reason I'm doing that is because of gaps in the data. So go back up to maybe the data visualization and I can draw on it. What would be a good example? Okay. 20. We're doing 22, aren't we? 22. In this case, I guess it's a poor example because there really isn't much excursions over 22. But that function will actually create little rectangles between points and then sum the amount of area that's above this threshold of 22. And it'll do the same thing for PBTO2. And I believe that's slightly different than what was provided in the metadata table. The threshold that they provided was on 20, which was the old ICP threshold, whereas what I'm doing is on 22. Yeah, so let me go back down to where I was here. Yeah, and the way I'm doing this, I'm effectively iterating over all data points in that data frame, and I'm finding the current time and previous time, using that to calculate the what I call dx, and dx is just the amount of time that has passed from the previous time value to the current time value. And then I'm calculating the excursion over the threshold by subtracting either the threshold by the point value of ICP or the point value by the threshold, whether it's less than or greater than. And then I'm multiplying those together. And if dy is negative, then I don't consider it, because then that means that it's not on the side of the line that I actually care about. And then this function returns to me the area. The next function I'm designing is the percentage of time exceeding threshold. And this is much simpler. It's just the amount of data above or below a threshold divided by the number of points. The pro of using this, as opposed to using a data set right off the shelf, is I have control over the values that I provide to it. So I could set thresholds and change them in a way that I can't do so with this summarized feature set that I got from an Excel file. I can actually rebuild the feature set using different thresholds if I really care about, which seems obvious, but it's just an example of how powerful the feature engineering technique is. So the first thing I'm doing is I'm taking that pivot table that we created and I'm renaming the columns to make it easier. And what we have is this is the same pivot table. And I believe this is what it looks like for ICP. So it's just the value in time. And I created a function that will actually iterate through that data set, or all the patients, to derive, in this case, 8 features. 8 features in this case, instead of 9. And this took a long time. So I did this in advance, but I'll explain to you what this block of code is doing. So for each patient, it's extracting the target value, which is the GOS-E that we're trying to predict. It's skipping any patients that have that don't have an outcome, because we don't want to predict something that doesn't exist. And then we're grabbing the ICP and PBTO2 raw data, computing the area above and below thresholds for ICP and PBTO2. And then I'm throwing in a nonlinear feature by multiplying them together. So I thought that I'd engineer a feature that is a nonlinear combination of 2 of the other features. And that's pretty powerful, because most machine learning algorithms, most models assume that coefficients are linear combinations of one another. there's some degree of nonlinearity with neural networks, but they don't do it in quite this way. Then I'm in a study group, which is just which group they're in. And then I'm grabbing also the days of ICP monitoring and days of PBTO2 monitoring. I'm using that as a feature. And then I'm also using the percentage of time exceeding a threshold for both ICP and PBTO2. And now I can bring the features together. I'm bringing those first three features together in a little array. And then I'm doing something called one-hot encoding. So I can't throw a categorical or nominal feature into a neural network because it doesn't know what to do with a string. So I have to either take the categorical variable and assign its levels to values. So maybe like ICP could be 1, ICP and PBTO2 could be 2. Typically, when you have a nominal variable, you want to separate it into a one-hot encoded vector where where each level is a different vector. So I have 2 levels for this one variable, ICP only, and then PBTO2 and ICP. So I'm using 2 elements in a vector to establish that 1, 0 is ICP only, whereas 0, 1 is PBTO2 and ICP. And that's just, it's better in cases when you're trying to translate a categorical variable into a feature vector for training. And then I'm pushing in the other variables that we have here, 5, 6, 7, 8. And then I ran it for all the patients, and it looks like a giant array of numbers. A 2D array where each item in the array is an array of features that I just defined, x1 through x8. I saved that data, put some columns, and then I'm going to load it back in, and this is what we have. We have ICP burden, PBTO2 burden, the nonlinear feature that I did, which is just a multiplication of these two, then the one-hot encoded feature right here, the days in ICP and the days of PBTO2 that I got from the metadata table, and then the other function, which was time below a threshold and time above a threshold. And this is 9 columns, so it's 9 features that I'm looking at. So the same number of features I had before, but I engineered some of them. And we're using that same plot and trend function that I created earlier to verify that the features are contributing different information. So these two do not have a high similarity, which means that they're not that they can be used in the data set. If they were highly correlated, I wouldn't want to include them. Same with this one. Same with this one. I just plotted a bunch for eye candy. And then this is the output, which is the same as last time. It's the GOS-E on a scale from 1 to 8. And then I'm just binarizing the values same as I did last time. And then I can run the k-fold cross-validation like I did before. And you'll notice that the F1 score is slightly better at 28.3. I ran it again. I think it's 28.3. I think I got it up higher, but it's pretty consistent time to time. And that is what I wanted to highlight in this session. The main topics that I covered, or I tried to cover, were the importance of visualizing data, which we covered in the last session, as well as the importance of feature engineering and how feature engineering can influence the model's outcome. And that's why, as you'd expect, data scientists spend a lot of their time up here, and then the model selection and model training ends up being a very small detail after the data is curated and really well put together. I would love to open the floor for questions. This is a really simplified use case, and it'd be cool if anyone had ideas as to how we could improve the model with the data available. There are some metadata that I haven't included. I haven't looked at any other threshold excursions except for 20 and 22 for PBTO2 and ICP, respectively. But I hope this was helpful. Greg, do you have any comments?
Cool. So thanks very much. I was just going to say thanks very much. And if anybody has any questions, please put them in the Q&A chat. Well, wait a minute. Oh, this is cool. It's nice to be getting into using some of this real data to look at real problems and show examples of how it can be used. I think we're getting to the point now where we have the ability, and people are building these data sets, and so it's just a matter of turning loose the the smart people with the data and the tools. First question in the Q&A. Can you do this in real time to manage a patient?
Good question. So the model you deploy in real time, what model you deploy in real time is heavily influenced by the task you're trying to target. So right now, the task is pretty far out. Sure, you might be able to create a score that of how the patient is predicting, maybe predicted to go into a higher GOS-E or have a better outcome, but it doesn't really give you any actionable intelligence on what to do to move them to the desired category and move them from a bad state to a good state. So sure, you could build an algorithm and deploy it. However, it's very specific to the task at hand and the problem definition. And for instance, deploying this one in real time would be incredibly difficult because I would have to know the days of ICP monitoring, and this assumes the amount of days of ICP monitoring after the patient has undergone neuromonitoring. So because I'm training on a data set that from which the patient population is all retrospective, I would not necessarily be able to translate that to real-time use. I would have to build a model that was used in a more real-time-ish way in order to bring it to that use, if that makes sense. It would be biased toward the retrospective nature of the data that I'm using to train it.
Yeah. So you have to build the model on the data that's going to be available to you in real time.
Yes.
Right?
Yes, that's the main idea.
Cool. Another question. Usually we visualize, usually we visualize data in the frequency domain. Do you have experience visualizing data and selecting metrics in the frequency domain?
Yes, we do. This data, I'm pretty sure, I'm looking at what, a minute at a time. And it's unlikely that we would be able to, it's unlikely that we would find, in my opinion, it's unlikely we would find informative features for data of that resolution. I think it'd be more relevant, the frequency domain feature extraction would be more relevant in terms of more periodic signals or higher frequency signals, like any of the ECG waveforms, ICP and EEG. Doing an ECG use case or a EEG use case in the future would be very interesting, in which case we would introduce more frequency domain features. Right now, the time domain is what we care about because that's typically what people use for interpreting the signal just kind of on a day-to-day basis, right? If you only have the number of ICP collected every minute, you're only going to be able to understand what's going on at the time domain. As you scale down to something that's on the more waveform level, where you care about what the ICP waveform looks like, then I could see it being justified to look at the frequency domain. So it's heavily dependent on the data that you have available and what you're analyzing.
Yeah, it would be. I mean, we do have that level of data for in this cohort. So it would be cool to in future webcasts do something where we are looking at the shape of the ICP waveform or something like that. Would be really cool. There are two more questions, actually the same question-ish twice, and I wanted, and this is something I was going to cover. asking about the availability of the notebooks and the data. Yes, we were supposed to have had this stood up yet, but we are trying, we're in the process of building out a website that you will all be able to go in and download both the notebooks and the sample data. It's just taken us a little bit longer. We had when we have online systems running and you're trying to merge changes and get things sorted out, you kind of have to, we had to do things in order, and it slowed down the process of us getting that out, but we are going to do that very soon.
And then there's a question about, well, one thing I'd like to add, Craig, is the data will be, right now I'm viewing the data in kind of like Matplotlib, but we have our own web-based viewer that allows people to actually review the data in a pretty slick and integrated way. And so all the patients that we're using here, you'll also be able to review their data in some capacity on that system as well. We have another question, whether the data besides ICP and PBT02 that could be used from the Boost2 data set. Yes, I think the reason why I've focused on these two is because it narrows the scope, A, and B, that's what Craig had pre-processed in the last webinar. So I'm just going along, but the Boost2 data set I think has a lot of vitals. I think we have imaging as well from Ramon. So that there's a lot of opportunities with this data set that have yet to be explored, and part of the reason is because it hasn't been opened up for people to use it, and that's what we're trying to help out with. And then Baptiste asked if he said that respiratory or slow changes could be evident in the signal, and you're absolutely right. So in signals that are affected by things that have more of a lower frequency effect, like by the respiratory system, definitely could be affected, and you might be able to capture that in the frequency domain, and that would be an interesting feature to explore. And then the other question is whether the data set will be higher than 1 minute, whether the sampling rate will be higher than 1 minute. Craig, do you remember if there's waveform level information in the raw data, I'm assuming, yeah.
Yeah, there is, yeah.
Yes. So
we'll
there
have
will
to
be.
double check that. Well, I'll have to double check that that's in our, that we've got permission to do that, and not just the data that we use to build these things.
Yes.
So we'll have to look at how much we can. It's probably fine, but I do need to go ask.
Yeah.
Yeah, most likely.
Another question is whether I can estimate the amount of time I spent data cleaning. Well, I spent not a lot of time cleaning data, and that's reflected. I didn't spend a lot of time in cleaning data and engineering features, and that's reflected in, you know, the score I got, right? So I got a 28.3%, and I reckon that if I did a better job at cleaning the data, this score would go up. The features I'm calculating are highly influenced by the artifacts in the signal. So if we look back at the raw data here, you can see that there's a lot of artifacts that otherwise would not be there if I excluded them. So I could reasonably say that I don't care about this, I don't care about this, I don't care about this. And if I remove them, that would influence the features and may have an influence on how well the model performs. So you can see that it follows that the more time you spend cleaning your data and understanding, oh yeah, we can extract features from, like we can extract frequency domain features, like Baptiste said, that the more time you spend on that step, the better that your results will be. So I would say that my model results are congruent with the amount of time I spent cleaning my data, if that's what you're wondering about.
Yeah.
Oh, right. Okay. Yeah, I guess the reason I showed this was to emphasize the amount of time that where time is often distributed for like the tasks like these. So I mean, I just grabbed this from like Google, but it's effectively what you would expect a data scientist to take. You know, like when you aggregate kind of all machine learning efforts or data science efforts.
Yeah, you see a lot of pictures like this
Like
kind of
that.
out there,
Yeah,
and
it's very common.
they're based on samples, questionnaires of people who do this for a living, and they get the people that say, well, how much time do you do this? How much time do you do that? And overwhelmingly, the
Yeah.
actual data science, the actual machine learning is a small percentage of the of a data scientist's time. So
How many patients? I believe that after I removed null values, there was 100. So this is after I removed the null values, there was 100 patients that I used in this data set. So I think I split the training and test set 80-20. So 80 patients to train and then 20 patients to test. And then I also like having a validation set. So usually I would do like a 70, 15, 15, 70 for training, 15 for testing, and then 15% for validation.
so what's the difference between validation and test?
It's a good question. So I didn't understand this at first either. And effectively, well, the training set is to build a model, and the test set is to test a specific instantiation of that model on that data set. And then validation is used for when you change hyperparameters. So if you're doing hyperparameter tuning, you don't want to be influenced by the same data that you're using to test it, because there might be confounders. So you use a completely different test when you're asking questions about the hyperparameters of the model. That's at least how I see it.
Cool.
So if you're dealing with the number of hidden layers, the number of hidden units in a hidden layer for a neural network, and you're modifying that, you would do that on the validation set. From what I understand.
Yeah.
Cool. A lot of good discussion. I really appreciate this.
Yeah,
And
thank you everyone for the questions.
This is by no means perfect. It's just a simple it's a simple demo of how the process is supposed to work. And this process can be shorter. I mean, the results aren't as great, but if it's longer and you're smarter about the features you engineer, then you end up building a model that is really worth your while.
All right.
Cool. Greg, do you have closing slides?
I just had the one for just to yeah. There it is. Sorry. So yes, we are going to be, you will be getting an email with an ID and a password to get onto this demo site that will have all of the assets. And also, please, if you want to screenshot this, sign up for our newsletter. If you have any questions, reach out to myself or our info@moberganalytics.com. And just thank you all very much. We really appreciate everybody coming in, everybody staying late, and especially the questions. The biggest value for us is talking to people like you and understanding what you're trying to do. Like I said, our mission is to help build the tools. And if I have no idea what kind of house you're trying to build, I don't know what tools you need. So we really appreciate your engagement and involvement. And we hope you all have a very wonderful and safe holiday. And thanks very much.
Yeah, thank you very much. Someone left a comment about where is Dick? Say happy birthday to me. We'll let him know. He's probably watching, but we'll let him know.
He's here. He's lurking.
He's here. He's around.
We stole his webinar too. So
yeah,
he can't log
in.
Thanks everybody.
Thank you. Have a good one.